It can help a lot, even in solving some questions related to the topic. The first thing I want to clarify is that in the X-ray tube, there is a cathode and an anode. The cathode, as I mentioned, is connected to a specific electrical circuit. This electrical circuit carries an electric current, meaning it has a current flowing through it. When we talk about filament or cathode, it is also carrying an electric current, which means electrons are moving and circulating inside the wire or filament. So this movement of electrons creates a current, which I call filament current. The filament current represents how much I increase it. The more I increase it, the more electrons are liberated at the surface here in large quantities. Now the filament needs a voltage to operate, and this voltage is relatively small, reaching about 10 volts. In order for these electrons to move and gain kinetic energy, they travel through the wire of the filament itself. So I have filament current and filament voltage. Let's pay attention to these: filament current and filament voltage. The idea behind filament current is that when it increases, the number of electrons liberated from the surface of the filament also increases. And what happens when the filament voltage increases? It provides more energy to the electrons, which also leads to greater heating, thus increasing the number of electrons. Therefore, when filament voltage or filament current increases, it increases the number of electrons that will vibrate on the surface of the cathode. Is that clear? Now, these electrons, in order to move and go to the anode, their movement from the cathode to the anode creates a current, which is called tube current, and its value is measured in milliamperes. While the filament current is measured in amperes, the maximum value can reach around 10 amperes, which is very high. As for the tube current, it ranges from 0.5 milliamperes to 1000 milliamperes. The current that moves the electrons from the cathode to the anode is driven by the voltage that I apply as a potential difference between the cathode and the anode, which I call tube current. The tube voltage is my kilovolt value, which can be 20, 30, 40, 50, 120, or 140 kilovolts. The function of the tube voltage is to provide kinetic energy, thus controlling the energy directed towards the electrons and the energy of the X-rays produced. Therefore, an increase in tube voltage, U voltage, leads to an increase in the kinetic energy of the electrons when they receive acceleration. An increase in the filament voltage connected to the filament results in an increase in the number of electrons. The element that connects to the filament, it increases the number and fluctuations. When the number of electrons increases, it works, with a greater number of atoms at the anode, further increasing the number of electrons. This enhances the laws or effects of the influence. Thus, filament voltage affects the influence, and tube voltage affects the influence of electrons, resulting in more imaging. If the filament current increases, the number of electrons moving across the filament will increase. To increase the tube current, you need to increase the filament current to provide a greater number of electrons moving from the cathode to the anode. Therefore, the filament current is highly dependent on the tube current, while the tube voltage is unrelated to the filament voltage. You must distinguish between the two. The filament voltage is what heats the electrons inside the filament circuit, while the tube voltage is applied externally to accelerate the electrons from the cathode to the anode. I hope this is clear for you in answering the questions. So, what are the other points that might need discussion?
The second point is the other needs.
the anode. Inside it, there are atoms. For example, tungsten has K shell and L shell electronic shells around the nucleus. The electron present in the K shell has a certain binding energy of 70 kilo electron volts. The electron coming from the cathode needs to have an energy of 70 kilo electron volts or more in order to perform the removal or knockout of the electron in the K shell. In order for it to create a point, or if it can't do that, what does it mean? It means that the electron must come with energy equal to or greater than the binding energy of the K shell to be released. Then, another electron from a higher orbital comes to fill the gap that occurred and produces the characteristic X-ray. Now, if the characteristic X-ray comes from the electron in the higher energy state coming from the K shell to fill the K shell, I call it K alpha. If it comes from the M shell, I will call it K beta. So, which one has higher energy? The one coming from the higher orbital, K beta, has higher energy. This means that the difference in energy between the M and K, which is for K beta, is high. The difference in energy between the two energy states is significant, and we said that the X-ray emitted carries energy equal to the difference between the binding energies of the two energy states. That's why the X-ray of K beta has higher energy than the X-ray of K alpha. Why? Because the alpha emitted between the two energy states has a smaller difference between them. The difference in energy state between M and K is significantly less than the difference between L and K. This is indeed also a crucial piece of information that I would like you to focus on, to make it clear for you. Characteristic X-ray is a distinctive feature of the material itself, meaning it does not depend on anything other than the material itself. For example, if you use a material with a high atomic number, the binding energy will be high, so you need a high applied voltage to be able to release the electron present in the K shell. This is characteristic of the type of material present in the characteristic X-ray. As I mentioned earlier, I have something called tube voltage that I was talking about a moment ago. There is something called filament voltage that affects the number of electrons. Increasing the number of electrons will always increase the number of X-ray photons, whether they are characteristic or K alpha. Initially, we increase the number, and in the cathode, when it increases, it will consequently increase. Whether it was characteristic or it was. Tube voltage provides kinetic energy that supplies energy from the characteristic X-ray photon. It primarily depends on the tube voltage. If the incoming tube voltage is not high enough, greater than the binding energy of the K shell electron, then you won't be able to remove it, and thus you won't be able to create it. Now, regarding the number of X-rays, specifically the characteristic X-rays, their voltage rate or intensity or amount does not depend on the tube voltage. It is related to the energy. However, it does depend on the filament voltage. Why? Because the filament voltage will provide a large number of electrons on the filament, which will consequently increase the chances of interactions. Therefore, the rate or amount of characteristic X-rays produced will be high. The second type of interactions that occur is considered X-ray.
I am X-ray. I have an electron coming from the cathode that interacts with this around it and produces a photon for me. The closer the electron is to the characteristic X-ray nucleus, the higher the energy it will exhibit. If it interacts with the same nucleus, it will show the highest energy in the spectrum, which is kVb here, or pKv that I want to set on the device at 120 or 42, or I consider my values if they increase. The atomic number of the material increases with the increase in the thickness, which increases the intensity or quantity of the X-ray photons that will be produced. You will find that your spectrum enlarges as a result of the increase in your atomic number, which increases the probability of interactions. In this case, you have a thicker spectrum or a higher intensity of X-ray. Another important point is that the filament voltage and tube voltage affect the number of X-ray photons. The filament voltage increases the number of X-ray photons, while the tube voltage also affects the number, increasing the number of X-ray photons present. This allows the electrons to interact effectively. Now, one of the things I want you to pay attention to in your lectures is that if I have X-ray photons, a group of photons like this, let's assume that all these photons carry the same amount of energy. I have placed a thickness of a specific material here, and we will call this thickness the half-value layer. This means that the thickness can reduce the intensity of the radiation incident on it to half of I node, which is the incident intensity, and this is I, which is the transmitted intensity. The more I increase the thickness of the material that can attenuate the radiation, the more the transmitted radiation decreases. That's why you will find a relationship between X, which is the thickness of the material. The more it increases, the more it decreases, decreases, decreases like this. All right, at a certain thickness, I reach half. The thickness is called the half-value layer. If all my photons carry the same energy, all of them 50 kilo-electron volts, then the thickness that will stop or reduce the incident radiation for the source will be referred to as half-value layer 1. It will be equal to the half-value layer 2, meaning the transmitted radiation that passed through the first half-value layer will be reduced. To reduce it again by half, you need the same thickness in the case of dealing with monoenergetic radiation, where all the energy is the same, like all being 50 or all being 40. However, this is not the case with X-ray. X-ray produces different energies, such as 10, 20, 30, 40, which we refer to as polyenergetic. So you have photons with high energy, and photons with low energy, and some with very high energy, which increases the frequency, giving you a range of energies. Now, when I place a thickness of a certain material, let's say lead, this thickness will start to remove the soft radiation, which are the initial energies, for example, from 10 to 20. So, who will pass through? High interactions, such as those at energies of 30, 40, and 50, have a very high frequency angle. Now, regarding the initial thickness, which has low intensity of radiation, we refer to the half-value layer, or the individual layer that includes half the half-value. As we were talking about intensity, the total amount of energy of photons per unit of area at a time, it's not the total number. I'm not talking about intensity here as a count. Rather, it's the total energy, which I refer to as energy flow rate. Just as we discussed in the inverse square law. When I place the weight, here the energies are high, for example, from 30 to 120. The towers have high production. Whereas the production of the towers here was from 20 to 120, or from 10 to 120. The towers were operating at 60 kilovolts in the first area, yes, but in the second area, no. So you are talking about energies from 30 to 120, which means you are discussing approximately 75 kilo-electron volts continue to exist if the energy is high. Of course, to stop this energy effectively and efficiently, I need a larger thickness, meaning my half-value layer, or perhaps even more so. The second half-value layer must indeed be larger. This is indeed what happens. In fact, the second half-value layer with polyenergetic beams is significantly larger than the first one, because photons that passed through initially underwent beam hardening processes, removing all soft radiation and only allowing high energy radiation to pass through unimpeded. This higher level of energy has a considerably larger average, increasing its effective overall impact. So naturally, a much thicker barrier is needed to stop at least half of this potent form of energy. Therefore, in these circumstances, the second half-value layer can rightfully be considered substantially greater than its predecessor. The higher attenuation coefficient, which depends quite significantly on material density, means that denser materials will have correspondingly higher coefficients. If the electron density is high, it means that it can interact significantly with the radiation, resulting in a large attenuation coefficient. The larger the attenuation coefficient of this material, the less thickness I need to stop the radiation. Therefore, there is an inverse relationship between the half-value layer and the attenuation coefficient. You will find that the half-value layer of lead has a very small thickness, much less than that of wood, which has a slightly higher density because it requires a larger thickness to stop the same radiation that lead can stop. The thickness of lead can achieve attenuation. Thus, there is an inverse proportionality relationship between the attenuation coefficient, which is the linear and attenuation coefficient of the material itself. The attenuation coefficient, if you relate this to the density of the material, will create something called the mass attenuation coefficient. There is an inverse relationship between the half-value layer and the attenuation coefficient. Also, the energy is a point of consideration. The text is unclear, meaning in Arabic. No meaningful translation can be provided. Regarding the X-ray photon or my tube voltage in the X-ray tube, if it is low, the X-ray photons will be emitted with low energy. In this case, the half-value layer that can stop them will be thin. It will be small enough to stop them. There is a relationship between the tube voltage and the half-value layer. The higher the tube voltage, the larger the half-value layer needed to stop X-ray photons. Conversely, if the tube voltage is low, a smaller half-value layer is required to stop the X-ray photons. Additionally, regarding the Compton interaction, I always mention that Compton interaction is dominant at high energy compared to the photoelectric effect. The photoelectric effect is more significant at low energy, with low energy levels and high density materials, particularly those with high atomic numbers.
The photoelectric effect is considered dominant over Compton scattering. The photoelectric effect involves an interaction between the photon and the innermost electron, the electron that is located in the region close to the nuclei. For example, it can cause a knockout, resulting in an electron being ejected from the atom, which then emits a characteristic X-ray. Alternatively, it can transfer all its energy to the electron, in which case the electron is referred to as a photoelectron. The emitted X-ray, as mentioned, can collide with another electron while leaving the electronic shells, transferring energy to that electron, which is then called an Auger electron. Thus, when a photon collides with an electron, it transfers all its energy to it. An electron remains in motion with the full energy of the photon, which is called a photoelectron. If an electron drops from a higher orbit, it fills the vacancy and emits an X-ray. This X-ray is produced when another electron gives all its energy to it, which is referred to as an Auger electron. The photoelectric effect is directly proportional to the atomic number raised to the third power over energy raised to the third power, meaning energy cubed. Additionally, the probability of the photoelectric interaction increases with the cubic increase in the atomic number. The same idea applies to the reduction in energy, which enhances the photoelectric interaction. When energy increases, low energy Compton scattering also occurs, and as energy increases further, Compton scattering happens, but to a lesser extent. However, the reduction here is not significant, meaning you could say that as energy increases, Compton scattering decreases, but it is not significant. When you compare it to the photoelectric effect, you will find that Compton scattering is more dominant than the photoelectric interaction, especially in what? Not with the electron density matter, I mean the photoelectric and Compton scattering, because it deals with the free electrons that are present, or the outermost shell electrons. It depends on the ratio of the electrons that are present, the free electrons inside the shell. The more the electron density increases, the more the number of electron density increases, the higher the likelihood of Compton scattering and its occurrence. It is directly proportional to electron density and inversely proportional to energy. However, the reduction occurs in Compton scattering, which is significant. That's why, for example, in soft tissue, the components that have tissues consider Compton scattering to be dominant and depend on the outermost shell electron. It gives part of its energy and undergoes scattering, taking part of the energy from the incident photon, which is called the recoil electron. The photon that underwent scattering is also affected. And what about the photon that underwent scattering? Everything that is scattered at a large angle means that its energy is high. So, if the incoming photon, such as one that is falling, has high energy, you will find out clearly enough that indeed even the scattered photon also possesses similarly high energy levels too, right? Here in this scenario, it depends on precisely what kind of initial starting point or level of energetic force was present within said incident photon, which originally fell downwards initially upon impact itself. The angle here gets determined based entirely upon how much total amount, overall energetic capacity it actually contains inside itself. Alternatively speaking, another way around, gives me an indication regarding its specific measurable degree concerning current existing power status level thereof accordingly. That's why, exactly, for instance example, purposes only specifically when considering low energy X-ray photons, whenever they strike against patient's body, it gives you side scattered photons more than forward scattered photons. What does that mean? It means that the patient can produce the X3 photon that strikes the patient and interacts. This interaction can be Compton scattering. So, what about the angle of the scattered photon? With energy, you find that the ratio of side scatter which is not in the direction of the film or the receptor, is higher than that in the direction of the film. And with high energy X-ray, you find that forward scattering is higher. The forward scattering here is higher than the side scattering, which is why you will always find that with high energy, the forward scattering is greater in the direction of the film. This causes what we were talking about, the distortion, or it reduces the contrast present in the image or the image of the film. On the other hand, low energy increases the side scatter compared to the forward scatter. The energy provides considerably more forward scattering than side scattering, and this is indeed because, as I mentioned, the higher the incident photon energy you have, the larger the scattering angle of the photon will be. This is because at that time it carries a significantly large amount of energy. So you will find that the forward scattering will be proportionally higher with high energy compared to low energy X-ray.